Hello everyone. The topic of my thesis is data generation method for disease prediction on imbalanced data. The first part is introduction. I'm going to introduce the background of study. Predicting potential disease is crucial to preventing extreme disease progression and maintaining human health. However, in many cases, it's difficult to obtain a very accurate prediction by relying only on doctors. Therefore, the most advanced machine learning technology can be used to predict the possibility of suffering from a certain disease based on the patient's clinical data and genetic information, more accurately identify and predict the development turn of the disease, and contribute to early intervention of potential diseases, formulate treatment plans for patients, so as to obtain better treatment results. Although disease prediction has good development perspectives, it still faces the problem of data imbalance. Data imbalance refers to the uneven distribution among categories in the dataset. Some categories have far more data than other categories, while some have relatively free samples. In disease databases, there is often a large amount of data for common diseases, but the number of samples for rare diseases or diseases with specific conditions is often very small. Due to data imbalance, disease prediction models often favor the majority categories and ignore the minority categories. This is likely to have a serious negative impact on the performance of the model, causing doctors to miss cases that really need attention, and even lead to misdiagnoses of diseases. Regarding the problem of data imbalance, although algorithm modification can balance the impact of different categories, it's not general enough. So this study chooses the method of generating artificial data for categories with a relatively small number of samples to solve this problem. However, oversampling and undersampling methods have very obvious shortcomings. Therefore, this study adopts a more effective method of building a generative adversarial network or its variants to improve the performance of the model. The main goal is to study how GAN generates data of imbalanced categories, compare multiple variant methods, and find the best performing model, thereby improving the accuracy and stability of disease prediction. The specific implementation steps of this study include collect clinical data and genetic data and process them, explore oversampling and undersampling methods, and analyze their advantages and disadvantages. GAN and its variants will be studied in depth, and the framework and parameters will be designed. Use Python for data analysis and model development. Combine with PyTorch to implement GAN and its variants, and use XGBoost to predict the generated disease data. Finally, evaluate the respective model performance using different data generation methods. The study is not going to delve into other methods of processing imbalanced data, but instead focus on generating data using GAN, and it also includes something that a study doesn't do. It doesn't involve detailed discussion of other imbalanced data processing methods, such as ensemble learning, weight adjustment, and so on. Specific deployment and computing resource issues in real-time clinical applications are not discussed. It doesn't solve all possible problems, such as not considering the specific calculation amount of all GN models. There are also various limitations in the research. Rely on data provided by hospitals, research institutions, and so on. The quality and the completeness of the data are limited by the data source, and there may be missing data or outliers. In-depth research on JN and its variants is limited and doesn't consider all possible variants and models. The performance metrics chosen may have certain limitations and may not cover all aspects. The tasks mentioned in the schedule need to be completed within a limited time, which may limit the depth and breadth of the experiment. The generalization ability of model performance may be affected by specific dataset characteristics and may not necessarily apply to all disease datasets. I briefly introduced the structure of the thesis. It's roughly divided into 6 chapters. The first chapter briefly introduces the background, purpose, and content of each chapter of this study. Chapter 2 will review the relevant literature and introduce in detail the current status of disease prediction, data imbalance issues, and research on data generation methods. The research methodology will be introduced in Chapter 3. This section will not only describe the disease prediction dataset, including the degree of imbalance, but also introduce JAN and their variants, machine learning models, and deep learning frameworks used. The next chapter describes how to use Python and a deep learning framework to build and train GAN models, and how to use a machine learning model to make predictions on the generated data. Chapter 5 will present the experimental results and compare the performance of different methods. The final chapter will summarize the main findings of the study and its contribution to the field of medical disease prediction, analyze the advantages and limitations of JAN, and explore future research directions and possible improvements. Okay, now comes the literature review part. Previous research has identified the problem of data imbalance in disease prediction. With the amount of data for common diseases in disease datasets being much greater than that for rare diseases. And previous research has also tried to use many methods to solve the problem of data imbalance. Among them, the first method that most researchers think of is to modify the algorithm. This method is to modify the existing model and obtain a prediction model with better performance without introducing noisy data and missing data. But it not only requires a deep understanding of machine learning and specific algorithm structures and pinpointing where the problem occurs, but this method is not very common, and different models often have different situations. Oversampling method balances the dataset by adding sample data from minority classes. It's divided into methods such as random oversampling, smooth, and undersampling methods balance the data set by reducing sample data from most classes. It includes random undersampling, clustering, Tomac linking, and so on. However, both methods have very obvious shortcomings. Oversampling methods have problems such as overfitting, generating noisy data, and sample overlap, where undersampling methods have problems such as information loss and low accuracy. Therefore, previous researchers have found a more effective, more general, and more accurate method. Building a generative adversarial network, GAN. GAN is a machine learning framework that consists of two networks, a generative network and a discriminative network. Generative networks generate data samples that are similar to the original data. The discriminative network determines whether the generated data is real or artificially generated. The data generated by the generative network are evaluated multiple times by the discriminative network and continuously updated, making the data continuously become more realistic until the discriminative network can't distinguish between generated samples and real samples. Therefore, GAN can generate real data and increase the amount of data in minority categories. Currently, this method and its variants don't have traditional problems such as generating noisy data and are very effective in improving the performance of disease prediction models. But there are still unresolved issues in previous research. There is still no precise answers to how to select the best balanced data set for a specific situation in disease prediction. Most data imbalance solutions may be effective on a specific data set, but how to ensure their generalization ability on other data sets remains an open question. Some GAN models are computationally expensive to deploy in real-time clinical applications, which may limit their use in resource-limited environments or devices with limited processing capabilities. There is no widely recognized gold standard in this area of research. The field of disease prediction and data generation is still evolving, and different methods and techniques may perform better in different situations. Therefore, researchers often need to choose appropriate methods based on their specific questions and data. In the method sections, first, clinical data and genetic data will be collected from hospitals, research institutions, health record databases, or other medical information systems, such as EPIC systems, MEDITECH, and so on. And then the collected data must be cleaned and pre-processed to deal with missing data, outlier, and noise, and to standardize the data. Describe the characteristics and imbalance of the data and explain the distribution of sample numbers in different disease categories. If possible, conduct a statistical analysis of the data and visualize the data. Then, we will explore some oversampling and undersampling methods and analyze their advantages and disadvantages. For example, random oversampling is to randomly copy minority class samples in the training set to increase their number. Although it's simple and easy to implement, it can easily lead to overfitting. SMOT is a synthetic minority oversampling technique, which generates synthetic samples based on minority class samples and inserts them into the dataset. It reduces the risk of overfitting and improves the generalization of the model. But at the same time, it's likely to introduce inaccurate samples. Another example is random undersampling, which randomly deletes samples from most categories to make the number of samples in the two categories more balanced. It can reduce computational costs and is suitable for large-scale data. But important information may be lost, resulting in reduced accuracy. There is also a clustering method, which uses a clustering algorithm to divide samples from most categories into multiple clusters and select representative samples. Although it improves the robustness of the model, it has limited effect on high-dimensional data or non-convex distributed data. In-depth study of JAN and its variants, such as DCJAN, WJAN, CJAN, and design their frameworks and parameters. The first one is deep convolutional JAN, also known as DCJAN, uses a deep convolutional network as a generator and discriminator to enhance the learning of the image features. Wasserstein JAN uses Wasserstein distance as a loss function to improve training stability. Conditional JAN introduces conditional information to make data generation more directional. Use Python for data analysis and model development, and will use libraries such as pandas and numpy for analysis. Use PyTorch to design the architecture of the generator and discriminator. Define loss functions, optimizers, implement JAN and its variants, and iteratively train the JAN model and generate synthetic data. And then use chargeables to predict the generated data and adjust the model parameters such as learning rate, tree depth. Choose performance metrics such as recall, precision, and F1 score. Use confusion matrices and ROC curves, and so on, to evaluate the performance of each model. Compare model performance under different imbalance rate scenarios. Then is a rough schedule of my work. Prepare and complete the recording of the thesis presentation video by mid-February, and complete the peer evaluation within the specified time. Complete the technical part of the thesis in the last 2 weeks of February and the first 2 weeks of March. Implement JN and variants to generate imbalanced class data, then develop disease prediction models based on the generated data, and then use appropriate performance metrics to evaluate, analyze experimental results, tune the model, and optimize their performance. Finally, it takes 2 weeks to complete the final report, and then consult with the supervisor to revise and improve the final report. And these are the reference of the presentation. That's all. Thank you for your listening.